Coding agent solved the stacks and queues LeetCode problem in 3 seconds. Clean code, correct push and pop methods, big O analysis included. So what exactly is your job now? Here is what a coding agent did not do. Look at WhatsApp's offline delivery system and say we must use a strict first in first out queue, because if we use a LIFO stack to deliver messages after a user is offline for 7 days, they will read the newest message first, completely ruining the conversation context. That decision made before any code is written is the one that guarantees messages arrive in the order they were sent. After this video, you will be able to make it. In the next 10 minutes, you will learn the judgment call, not just the algorithm, that makes you the one engineer who picks the right structure before anyone writes a prompt. 5 things you will own after this video. Why using a standard array to queue messages destroys the CPU. The core physics of LIFO stacks versus FIFO queues. The exact WhatsApp production constraint of a 7-day offline time to live. The reordering trap that destroys conversation context, and the survival skill, the exact judgment call AI misses. If you watch this video to the end, you will be able to answer an offline delivery interview question better than 99% of candidates who just grind LeetCode. Let us start with what breaks. Imagine Bob turns off his phone for a week. Alice sends him a message saying hello. The server buffers it in memory. Alice's first message arrives at the server and is pushed to the top of the offline stack. A day later, Alice sends a second message, "Are you there?" A junior developer or an AI prompt used a stack to buffer the offline messages. The second message goes right on top of the first one. Bob finally turns on his phone. The server pops the stack. Bob receives the newest message first, "Are you there?" A second later, he receives "hello." The conversation is completely backwards. If this happens across hundreds of messages over 7 days, the chat is unreadable. The naive approach breaks the product because it optimizes for fast memory insertion instead of preserving human conversational time. Now let us look at the physics. Why ordering is not just a preference but a mathematical property of the structure you choose. A stack is like a plate of pancakes. You add a pancake to the top and you eat the pancake on the top. Last in, first out, LIFO. But human conversation doesn't work like pancakes. A queue is like waiting in line at the grocery store. The first person in line is the first person to get served. First in, first out FIFO. If you mix these up in a messaging app, nobody can communicate. Here is how a queue works under the hood. You have 2 pointers. The head pointer tracks the front of the line and the tail pointer tracks the back. When a new message arrives, you enqueue it at the tail in O1 time. When the user comes online, you dequeue it from the head in O1 time. Every data structure trades one thing for another. If you try to build a queue using a basic array, removing the first item means you have to shift every other item over by one slot. That takes On time and it destroys the CPU. To get O1 performance, you have to use a linked list or a circular array. You are trading memory overhead for CPU speed. Let us look at how WhatsApp applies this in production. The WhatsApp architecture explicitly optimizes for conversational integrity. Let us trace how a FIFO message queue handles Bob being offline for a week. Bob is on a flight. Alice sends 3 messages over the next few hours. The Erlang router sees Bob is offline. It enqueues message 1, then message 2, then message 3 at the tail of Bob's specific offline message queue. The queue is persistent, likely built on something like Kafka or a custom storage engine, and applies a strict 7-day time to live constraint. If Bob doesn't connect in 7 days, the queue is dropped to save server space. Bob lands. He connects to Wi-Fi. His phone establishes a WebSocket connection to the Erlang router. The router detects Bob is online and triggers a flush of his offline queue. The queue dequeues from the head. It delivers message 1, then message 2, then message 3. They arrive on Bob's phone in the exact order Alice sent them. Context is preserved. If this kind of judgment call, mapping a data structure to human conversational time, is what you want to make confidently, subscribe now. every Saturday 1 DSA judgment call free. Now let us map this directly against the naive stack approach and see exactly where each one makes the wrong call. If your requirement is conversational integrity, a stack completely fails. It reverses the order of time. A queue succeeds because it preserves the exact chronological order of events. Stacks are not useless. If you are building an undo button or a call hold feature where you resume the most recently paused call, you absolutely want a stack. But for offline message delivery or any job processing where fairness matters, you must use a queue. Ask an AI to build an offline buffer and it might use an array and just pop the last element because it's faster, logically correct in a latent window, but it destroys the product. The engineer defaults to the constraint. The answer is not write the pop method. The answer is the constraint of human communication requires strict chronological ordering. Therefore, we must use a first in, first out message broker. That answer is the one that gets you hired. Full system, every component visible here, is the complete journey of every message sent while Bob is offline for 7 days. One clean view, every hop in order. Alice sends 3 messages. The Erlang router receives them and detects Bob is offline. The router enqueues each message at the tail of Bob's dedicated queue. Message 1 is first, message 3 is last. Strict chronological order. The queue persists for up to 7 days with a strict time to live. If Bob doesn't reconnect in 7 days, the queue is dropped to free memory. Bob lands. His phone reconnects to Wi-Fi. It establishes a WebSocket connection to the Erlang router. The router detects Bob is online and triggers a full flush of his offline queue. The queue dequeues from the head, message 1, then 2, then 3. They arrive on Bob's phone in the exact order Alice sent them, 6 hops. Human time preserved. You now own the architecture. Last piece, how do you walk an interviewer through this in 45 minutes? That is next. 45 minutes blank whiteboard. Most candidates jump immediately to naming a data structure. That is the first mistake. Phase 1, clarify the constraint. Ask the interviewer what is the maximum time a user can be offline. What happens if messages arrive out of order? Those two questions tell the interviewer the structure choice comes after the constraint, not before. Phase 2, propose the naive approach out loud. Say that a developer might use a LIFO stack or a plain database row because it is simple to insert. Then immediately explain why it destroys conversation context. The stack delivers the newest message first, reversing 7 days of chat. Proving why the naive path fails is just as valuable as knowing the correct answer. Phase 3. Introduce the correct structure. Explain head and tail pointers. Explain that NQ pushes to the tail in O of 1 time. Explain that DQ pulls from the head in O of 1 time. Sketch the 2-pointer diagram on the whiteboard. Name the persistence layer, Kafka, or a custom durable storage engine. Phase 4. Address the edge cases the interviewer is waiting for. What is the time to live on the queue? What happens if the user never reconnects? Does the queue grow forever? Why can you not use a basic array to implement this queue at WhatsApp scale? The answer to each question shows production level thinking. Finally, phase 5, the trade-offs. A FIFO queue uses more memory than a basic stack because it needs persistent ordered storage. Head and tail pointers add complexity. A plain array DQ takes O of n. Every one of those is an engineering tax you pay for conversational integrity. The engineer who names the taxes wins the room. Before this video, you knew queues were first in, first out. After this video, you know that an offline message queue with a strict FIFO guarantee is the contract that ensures messages arrive in the order they were sent, even after 7 days offline. The engineer who understands FIFO ordering builds the messaging system that doesn't reorder human conversations. That distinction is your survival skill. Next Saturday, recursion and the call stack. If a user replies to a quoted message 50 levels deep, and your server traverses it recursively without a depth limit base case, you trigger a Stack Overflow and crash the messaging thread. We will design the recursion that doesn't melt the server. Subscribe to ByteLearn For the complete One Engineer System WhatsApp DSA edition, one data structure, one real world constraint. Every Saturday, hit the bell. See you Saturday question. Which DSA concept surprised you most? Drop it below. I replied to the first 10